The purpose of this video clip is to explore the role of chemistry in fluid dynamics. So fluid dynamics is a discipline that studies the motion of fluids as well as the interaction of the fluid flow with the surrounding. Fluid dynamics is everywhere in our life, and in fact, for example, hurricane is basically a classical fluid dynamics problem. And if you threw an olive into a cup of cocktail, then you see this beautiful splash, and that is also a classical fluid dynamics problem. And even if we just breathe, then we actually inject a jet into the surrounding air, and that is another classical problem in fluid dynamics. So fluid dynamics can be very useful. For example, design engineers can study the airflow near a speeding car, and that can help us to decrease the drag experienced by the race car, and hence we can make it go even faster. And fluid dynamics can be just also purely fun. For example, we could study the air flows near a running dinosaur and envision how much drag this monster actually could experience at the top speed. And if we have a cup of afternoon tea, we could also wonder what would the flow near a slice of cake if we have a gentle breeze brushing our cake. So by and large, fluid dynamics has been studied and practiced for thousands of years. And most of the time, we focus on microscopic behavior. And it's fair to say that the classic fluid dynamics say neither individual molecules or their interactions. And this can be appreciated by looking at the governing equation of fluid flow, which is the Navier-Stokes equation. So here we show a Navier-Stokes equation for a classic Newtonian fluid. And on the left-hand side, we say the mass time acceleration term. And on the right-hand side, we say the various forces responsible for driving a flow. So now the key thing that you can observe from this equation is that the nature of the fluid actually are entirely encapsulated in two numbers. One is density, and the second is viscosity. So here we really don't see any individual molecules as well as interactions between these molecules. They are all hidden, packed, or encapsulated in these two very simple numbers. This is in stark contrast to chemistry. So in chemistry, most of the time or a lot of times, we are very interested in molecules, right? So how atoms are bonded to each other, and how if we have one molecule here, say for example, a lithium ion that is chelated by a very complicated molecule like this, right? So how their electron cloud actually will interact. So hence, really one key element or key aspect of chemistry that we really oftentimes are looking at individual molecules, their bonding, their interactions, and we care about specificity. And that is, if we have molecule A and we have molecule B, the shape and the size and how atoms are arranged make a great deal. And chemists are very obsessed in studying this kind of thing. And this is actually can also be appreciated by looking at the fundamental equation in chemistry, and that is the Schrödinger equation. So in this equation, both the wave function as well as the Hamiltonian are mostly, right, so people solve them or define them, explore them at a subatomic scale, right? And so here, really, the focus is a lot of time. It's at the kind of the atomic level, right? So here, things are very much oriented towards single molecules, or a lot of time. So now we say that on one side we have fluid dynamics where we really don't see individual molecules, or we don't care about their interactions as long as we get our density or viscosity correct. Well, on the other side we have chemistry that is relentlessly focusing on molecules and even smaller electrons. So it's fair to say that fluid dynamics has been largely separated from chemistry in the past. So this actually have served us very well. For example, a design engineer, when he tried to optimize the flow near a race car so that we can reduce the drag, right? He or she does not have to worry about the size and shape of the oxygen and the nitrogen molecule, and even less so about, say, for example, the vibration of the atomic bonds. So however, in the past decade or so, a lot of progress has been made in engineering practice that has significantly pushed the envelope of fluid dynamics. And this actually has forced us to take a look at the traditional paradigm where fluid dynamics is segregated from the chemistry. So in a series of videos, we would like to explore the role of chemistry in fluid dynamics. So in this video clip, we will explore the importance of chemistry in electroosmotic pumping. Electroosmotic pumping is a technique where we use electrical field to pump fluids. So envision that you have a glass channel. So if you put salt water, say sodium chloride solution into the channel, then the chemical reactions at the interface between the glass and the electrolyte will make the surface of the glass appear to be negatively charged, as shown here. So then this negative charge will attract the sodium ion inside the solution toward it, and well, it repels the chloride away. So the end result of this is that we have what we call an electrical double layer formed near the interface. This double layer can be a few nanometer to a few hundred nanometer in thickness. So now, because in this double layer there is the excess of positive ions, so if we apply electric field in the positive direction, this positive ion will go forward, and as they go, they bring the water molecule around them forward. So this will produce a driving force, and this will lead to what we call electroosmotic flow. And this kind of flow is very useful in pumping fluids, in particular if we have very narrow channels, because one unique thing about this kind of flow is that when you shrink the channel, the peak velocity does not change as long as the electric field stays the same. So electroosmotic flow has been used very widely in microsystems. For example, what we have here is so-called lab-on-chip devices. So essentially what this device does is it integrates the analyte collection as well as separation detection into a single chip. So conceptually, you can shrink a lot of very bulky microscale devices and the instrument into a single chip, and that can be very appealing for a lot of biomedical applications. So now, one way to describe this kind of flow or pumping is using the classic fluid dynamics. So the idea is actually quite simple. What we do is we would represent the wall, in this case a negatively charged wall, as a no-slip surface with a given surface charge density. So now the fluid is reduced to just a kind of continuum medium with a certain dielectric constant as well as viscosity, and ions are simply fired as point charges. So this whole picture can then be reconstructed using a Navier-Stokes equation for the flow, as well as the Poisson-Boltzmann equation for the ion distribution. So the prediction of these equations, which actually work reasonably well, especially when the double layer thickness is large, will lead us to say that, well, if the channel is wide enough so that double layer does not overlap, then we have a flat velocity profile, which indeed has been observed experimentally. So a question one could ask is, how good is this kind of prediction? In some more exotic situations? Well, it turns out that this kind of prediction sometimes does not go so well. So how do we check whether this kind of prediction goes well or not? In addition to experiment, what we can do is we can perform what we call the molecular dynamic simulation to study this. And one of the most bizarre phenomena that is reviewed from this simulation is a very simple question that we pose here, and that is, what if we flip the sign of the surface charge and the external electric field at the same time, while we keep everything else the same? So here, basically, we say that, well, if we make the surface charge from negative to positive, well, we make the electric field from the left or right to the left, what would happen? Well, in this case, what we can expect is that sign of counter ion in the double layer will be switched. Now we will have more chloride ions inside the double layer than the sodium ion. As such, the net charge, space charge or ionic charge in the double layer will be flipped. So now, because remember, we also flipped the sign of the electric field. So what we can expect is that the driving force for the flow will remain the same. So now if you go back to our classic fluid dynamics, in that case, we could easily conclude that the flow will be the same, right? So now the question, of course, is this a really good prediction? Well, we check that using what we call molecular dynamics. And so this is the kind of simulation where we resolve all the molecules involved here, say water molecule shown here, right, as well as ions, as well as the wall, all at molecular solution. So this kind of thing, although it does not capture all the chemistry, right, so it doesn't really say anything about how oxygen and hydrogen bond, but it did consider the molecular specificity of water molecules as well as the ion and wall, right? So that gives us more chemistry than classic hydrodynamics. So what would this kind of simulation predict? Well, here's the result. So if we have a charged channel with 0.13 coulomb per meter squared, right? So the prediction is such that the flow will have a peak velocity of, say here, of 5 meters per second or so. But now if we flip the sign of the charge to negative 0.13 coulomb per meter squared, and flip the sign of the electric field, the magnitude of the velocity increased a lot. In fact, the increase are almost by a factor of 3. So now this is something that you can never expect from a continuum hydrodynamics, as we have just explained. So why is that? It turns out that this is really something that has to do with interfacial water's behavior. So what we did was to understand this phenomenon, we set up a new kind of simulation where we have a channel, right? So the positive charge wall is on the bottom and negative charge wall is on the top. And we put water in here and we shear the water here by applying acceleration. And then we measure the viscosity of the fluid across the channel. What we found is that near the lower channel where the wall is positively charged, the viscosity is relatively high. And in fact, it's about a factor of 3 higher than that near a negative surface charge. So this would help to explain why when we have a negatively charged surface, right, so why the velocity of the fluid is much higher. It's simply because the viscosity is lower. But this does not explain why the viscosity is higher near a positively charged surface, right? It turns out that this is actually come from entirely the chemistry of water. So one of the signature of water molecule or the chemistry of water molecule is that because of the very different electronegativity of the hydrogen and the oxygen atom, so water molecule have a large dipole. And also because of their peculiar shape, right? So a water molecule will tend to align one of its OH bond with another oxygen atom of another water molecule to form what we call the hydrogen bond. So now in liquid water, one water molecule will try or attempt to form 2 hydrogen bonds by donating, serve as a donor. And then at the same time, it will try to accept 2 hydrogen bonds as 2 hydrogen bonds as shown here. So this will promote what we call tetrahedral structure of liquid water. And of course, this is just a type of water molecule. Because of thermal motion, it can never form this kind of perfect tetrahedral, which only exists if you get to ice. But nevertheless, the ability to form a hydrogen bond or to align the OH bond with another oxygen. So this kind of thing, if it forms a hydrogen bond, then it can greatly affect the property of water. For example, if it forms a very nice hydrogen bond with its neighbors, then the viscosity will tend to be higher because to perturb this fluid flow, to perturb the arrangement of water molecule to generate a flow, we need to break this hydrogen bond. So now what we found is that if you have a charged surface, then near a positively charged surface, because of the positive surface charge, then it so happens that the orientation of the OH bond of one molecule is affected or modulated by this positive charge. And this kind of modulation, it turns out that will try to facilitate the formation of hydrogen bond between neighbor water molecules. Now, if we go to the negatively surface charge, the situation is opposite. So in this case, the negative surface charge try to pull the hydrogen near the surface, and this both discourage the formation of hydrogen bond, or in some cases simply makes the hydrogen bond very strained. So this actually makes the hydrogen bond weaker. So consequently, what we can say is that by having a negative surface charge, we actually are reducing the strength of hydrogen bond near the surface, while exactly the opposite happens if we have positive charge surface. So now what we can see here is that this peculiar shape of the water molecule and the peculiar chemistry, and that is the oxygen is much more electric, has a much better electronegativity compared to hydrogen, right? So this, along with the modulation of surface charge, changed the ability of water molecule to form hydrogen bond near the interface. And this then affects the viscosity of interfacial water. As such, it affects the net pumping of the fluids. So this reminds us of the importance of chemistry, or chemistry of water, in the hydrodynamics. So if you are interested in learning more of this, you can go through some of the papers listed here, as well as the dissertation. Some of the ideas shown in the previous slide has never been published, but you can find them in the dissertation listed here, which was supervised by Professor Alulu at the University of Illinois. With this, we'll stop here. Thank you very much for your attention.